Welcome to my multimodal project slideshow. I decided to go over space radiation because I thought that'd be pretty interesting. So, this is how I did that. So, I was like, what should I really decide on when looking at space? And I was like, there's so many ideas and topics, and I was like, gravity, radiation, or other things. And with a lot of help and work looking through ideas, I ended up deciding on space radiation. So, that is the main topic of today. It took me a long time to actually find the paper until I finally stumbled upon NASA's SGR Papers page, and that is where I discovered the red risks for a journey to the red planet specific article, which is what will be going over today. Now, this specific article has 4 different items that it really goes over. The first one, which is the one that I will be focusing on, is space radiation health effects that include cancer, cardiovascular disease, and cognitive decrements. It also covers spaceflight associated neuroocular syndrome, behavioral health and physical health decrements, and inadequate food and nutrition. I believe all of those would be interesting, but I decided to focus on radiation, and there was a lot to learn with this. So let's go over some of the terms. So there's 2 big types of radioactive items in space that we really have to focus on. GCR, which is low dose rate galactic cosmic rays, which is basically just a constant low quantity stream that of protons that basically just flies from interstellar space from exploded stars, and those aren't very good for you. Unlike SPEs, which are solar particle events, these are much less common, but they also are much more pronounced when they're around. SPEs are solar particle events, and these happened when the sun's magnetic field just goes a little off. Because the sun is basically fully molten, at least to a point, it causes a lot of shifting of the surface and everything else, and since it's such a massive body, it has a lot of imbalances. So, how much radiation is too much? Just for some examples, I said that the ISS radiation doses can be 30 to 120 milligray is what MGY stands for. Milligray is basically the same as 0.1 rads. To help bring this a little more into terms, NASA's radiation exposure limit for astronauts is around 600 millisieverts, which is basically the same as 600 milligray. You can earn up to about a sixth of your limit from NASA in a 6 to 12 month stay on the ISS. So, onwards to these 2 radioactive items between GCR and SPEs. GCR and SPEs they're present at basically opposite times from each other. GCRs are present when the sun is mostly calm and is not throwing out a lot of solar flares. Because it's interstellar, it's just a constant low amount of protons just flying in. And there's also high charged energy ions, which are much worse for you, but I'll get on to those in a second. GCRs come in just when the sun is inactive, while SPEs are only really thrown out and have to be dealt with mostly by people is during high solar storm events. So, high charge energy ions are very bad for the human body because they can interrupt DNA, they can break double strands, and just kind of wreck your overall health. We don't really know that much on short-term or long-term radiation effect, but cancer is the big thing that we have to focus on with radiation issues. So, next thing I decided to look into was the current efforts by NASA, what they're really trying to research and look into so that we can actually fix this. So basically, NASA's current effort, they have a risk scale, which goes from green to yellow to red, and right now, everything about cancer is in the red. Long-term late effects are not on the menu just because there's a lot of other things to go over, but their main focus right now is short-term mission effects. So, future study of cosmic radiation, as we're discussing, NASA is hoping to associate cosmic radiation as much to terrestrial, which is just Earth radiation, as possible. We just really don't know a limit or safety steps to keep us from crossing too far and having short or long-term radiation effects. Um, there is a major risk of cancer, but there are also many other things that can happen with a high dose of radiation. Some of those radiation risks, other than just cancer, can be cardiovascular disease, central nervous system issues between the brain, the spine, as well as neurological disorders such as dementia and other items, and just general DNA damage. So, any of these issues arising during a mission could lead to catastrophic consequences, and finding a solution is very important. As we expand and go more into space, it'll be very important to understand the human limit and how to keep ourselves safe from radiation effects. We also have some animal testing of radiation, as well as it's said in the paper, what they call advanced human cell-based model systems, which I would assume is either a simulation or actual, basically a human cell just in a petri disk exposed to um, the items that actually cause space radiation in the first place. So along with that, connecting ground and space radiation would be really helpful, just because we know a lot more about ground radiation than space radiation, and if we're able to connect the two, then we can have much better and sooner medical treatments and ways to diagnose things and just keep people healthy either in space or on Earth. So, for my questions, what are the current radiation deterring methods we have between technology, medicine, and general health procedures? And then I asked, could we undo or heal a limited amount of radiation exposure with the right methods? So, um, that is everything I have for this presentation. I really hope it was beneficial.